Welcome to Electronic Specifier Insights, the podcast for electronics engineers. I'm your host, Paige West. In today's episode, I speak with Hussein Osman, Marketing Director at Lattice Semiconductor. Hussein outlines Lattice Semiconductor's role in enabling Edge AI and how low-power FPGAs are positioned in this space. I hope you enjoy this episode. Let's get started. Today, I'm pleased to be joined by Hussein Osman, who is the Marketing Director at Lattice Semiconductor. So thanks very much for joining us, Hussein. How are you?
Thank you, Paige. I'm doing great. Appreciate you having me on the show today.
You're very welcome. It's a pleasure to have you. And why don't you start by telling our listeners a little bit about yourself and your background?
Okay, so I'm by education an electrical engineer. I spent about 20 years in the semiconductor industry. I've been always a big fan of a very flexible devices like FPGAs. So I've been at Lattice here for about 8 years and focused on driving FPGAs into edge compute.
Fantastic. And for those of our listeners who perhaps aren't familiar with Lattice, can you tell us a bit more about the company?
Yeah, Lattice is a pure FPGA company. FPGAs are programmable logic devices that are able to implement basically any sort of logic within the resources available within an FPGA. Lattice has been in business over 40 years, and we focus on the small and the medium-sized FPGA devices. FPGAs are characterized by the size of the logic resources. The element is called a LUT, lookup table. And so, depending on how many lookup table a device has, it's characterized either as small, medium, or large. So, typically 1 to 10K is a small FPGA, 10K to 100K is a medium size FPGA, and above that is a large. This depends on who you talk to specifically, but this is roughly where Lattice is playing the small devices. We're the leader in terms of low power programmable. Our devices stay around for a very long time, and they're focused on small form factor and low power and programmability.
Fantastic. Now, Edge AI is going to be the topic of conversation today. So can you briefly outline for us Lattice Semiconductor's role in enabling Edge AI and how your low power FPGAs are positioned in this space?
Yeah, Edge AI is definitely a trend. We looked at last year just briefly to see how many devices have shipped in this area. We believe beyond your personal compute devices, a phone and a tablet and computer, there were about 500 million edge devices that were shipped in 2024. So edge compute and edge AI is something that is starting to grow significantly, and it is forecasted to grow through the rest of the decade here. So Lattice has an ability to sit in between compute and sensors and turn sensors into smart sensors. We can dig deeper into that, but that's where I believe Lattice plays the biggest role in turning sensors into smart sensors.
And what are the unique benefits of using FPGAs over other processing architectures for Edge AI deployment?
Typically, in a system, you would have all sorts of sensors that have to connect to compute, and compute could be a CPU or SoC type of a compute. Lattice does not, try to take over that role of the brain of the system, but assist the system by the ability to interface these sensors into the system via a wide range of IOs. So FPGAs have very flexible IOs in terms of connectivity to sensors. This can be your typical image sensor, could be LiDAR, radar, time of flight, all kinds of sensors. So our devices have very flexible IOs and ability to bring those sensors data into the system. And then we can run some additional processing within the device, whether it's traditional CV or some AI processing, depending on the system's need.
And Edge AI often requires trade-offs between power, latency, and compute capability. So how do your FPGAs navigate these trade-offs?
So For sure that in a lot of applications, the system would need to interface with the sensors and in processing of the data, be able to either process fairly fast and at the highest compute power possible, or just be in ambient mode and looking out to the world and trying to see what's happening and process that data in as low as possible. Our FPGAs have the ability to turn themselves into different power modes and ability to process, ambiently at 1 frame per second to just grasp what's happening in the world, or crank up the performance and run as fast as the image sensors or the sensors themselves, and ability to pull that data and run it as fast as possible. Again, the system designer has the ability to dynamically shift between those modes in an FPGA. So context switching between different use cases and context switching between the speed at which the processing is done allows the system designer a big flexibility in terms of how they want their latency and power to look like for the overall system.
And could you explain how your FPGAs deliver low latency for time-sensitive applications, especially in environments like smart factories or autonomous vehicles?
So, in smart factories specifically, the devices that we have are able to run inferencing on sensors in a sub about 10 millisecond range of time. This allows for an example in a defect detection type of environment, a factory to run faster and being able to acquire data from the different cameras that are available and understand if the items that are being monitored are going, are in good shape or they have defects on them. You need a closed loop implementation in this type of a scenario where you detect something that's bad, you want to get it off the line and focus on the next item on the line. And so the communication between the action and the detection needs to be deterministic. It needs to happen in a specific amount of time. It needs to happen in that time at all times. So the determinism of the latency in a lot of this application is actually more important than, how fast the latency itself, or the throughput in this case. So FPGAs are good making things work in hardware in a deterministic way. So you can run these type of defect detection capabilities as fast as possible.
And in smart manufacturing in particular, have you seen or do you have any particular use cases where you've seen where low power FPGAs have unlocked new capabilities?
Yeah, so the example I just provided was around smart factory, to demonstrate how latency is important in that application. There are other smart factory applications where we see our customers are deploying solution into. So, for example, the ability to understand the presence of the operator, if the operator themselves is compliant with certain requirements, wearing the safety goggles or hard hat or things like that. So, safety aspect of running a machine is very important to our customers. Also, overall the attention of the user to to the operator to what they're doing within the factory is an interesting use case that we can unlock. Identity of the user, is this the right operator, is it somebody else? And putting those together, we're enabling a more efficient, a more safe industrial, environment for operating machines.
And what about in the automotive space, particularly with ADAS or in-vehicle intelligence? How are you addressing functional safety and real-time responsiveness?
Yeah, in automotive, Lattice resides between a lot of sensors and the central compute, very similar to many other systems. And our job is to aggregate multiple sensor data, pre-process this sensor data, and provide to the central compute more or less the more important information. So offloading the central compute, allowing it to do more things, allowing it to be more cost effective and power effective. And we are able to then, do some pre-processing, including some AI processing, such as finding the region of interest in a field of view that's pretty wide field of view, and a lot of times dewarping the image for the central compute so they don't have to spend the time working on other algorithms and can be focused on the main task of computing. So I think you might be seeing a pattern in our discussions how Lattice sits in between the sensors and compute, and we're always trying to offload the compute and turn sensors into smart sensors, event-driven sensors, if you will, instead of completely always throwing a bunch of data toward compute and using up bandwidth. And that also comes with other issues like privacy and security in many cases.
Yeah, and that leads me on to my next question, which is about the defense applications. They often require strict power and security constraints. So how do you meet these requirements?
One thing I think FPGAs do fairly well is efficiency in terms of compute. FPGAs are parallel compute engines. They're able to do multiple things at the same time at lower frequency, which normally translates into lower power. So in defense type of applications, there's a lot of use cases where the system is battery powered, for example. And whether it's a camera on a helmet for a soldier, or it's an unattended ground sensor that's sitting around for days and days on a battery and looking for interesting events to happen, detection of a vehicle or people or animals that are across a certain border, and doing that efficiently, always on, and transitioning between states of performance and power is really important. You're looking out for motion at first. If motion is detected, then switch from that to processing at lower FPS without having to do too much and lose the focus on the actual event, then transition to doing things at higher performance to make sure, yes, this is an object of interest before sending a note or a message to the central compute that's available, whether the cloud or distance away to alert. So in terms of defense type of applications, we still focus on the power aspect of things, and we're able to do things on an FPGA in an efficient manner.
And coming back to Edge AI, one of the challenges is scalability. So how do your FPGA-based solutions scale across different nodes or use cases?
So what we've been doing since we came into the Edge AI area, which it happens for FPGAs very early on because we have silicon, we have devices, we don't have to go build a device. And we realize also that our devices have the compute structure that is equivalent to what you see today in modern ASICs built for edge inference. So we right away started working on tools that allow users to bring their use cases and scale it. Early on, we did a lot of education, and we ended up actually building our own full end-to-end solutions to enable the market. But as time went on, we built a more robust tool set that allows user to first tune the things that we built and spend years building, and two, to allow them to bring their own capabilities in and scale across the different compute requirements. We also partnered with the ecosystem partners across different end markets with focus on specific application to allow our customers to just leverage the solutions across all these areas and scale our capabilities, leveraging all these people that are around us. There's no way that we could have done all the work on our own. So we were definitely looking into the ecosystem and how to use them in scaling and allowing our customers to do more things.
And speaking of scaling your capabilities, I'm interested to hear what developments in AI models or edge frameworks are influencing your roadmap at the moment.
For a number of years, we've been focused on CNN type of models, focused on vision specifically. As vision transitioned from the cloud to edge, that was the main focus for us. And right now, I think we're at a very specifically very similar moment to what happened about 5 or 6 years ago with LLMs at this point and VLMs. So that's the big rock that we're looking at in terms of our next development milestones as these compute systems or these models make themselves to the edge. They scale in size. They're going from 70 billion to 7 billion to 1 billion to below a billion parameters. They will make their way into the edge devices. So you'll see LLMs that are specific for use cases that are on an edge device and always on doing things ambiently, doing actions in our behalf without the user even intervening. So that's really the big thing for us is how to enable better VLMs and LLMs and generative AI in general on edge devices efficiently.
And finally, then, where do you see the next biggest growth opportunity for low power edge AI? I don't know, say over the next 2 to 3 years.
Are you talking in terms of end markets or are you talking in terms of applications or
I think applications.
so I'm always a fan of applications where they actually have a purpose behind them. One, two, regulations that are driving the adoption into these applications is really interesting. And some of the things that come to mind is, within a vehicle, driver monitoring systems are really popular, and those are becoming a mandate at this point. And there's a lot of room for improvement based on what's out there today. So I think that's an area that's really interesting to kind of focus on and drive. I also like the medical field and medical area, and especially small, compact medical devices, making those smart within the device itself. And there's also privacy aspect of that comes in with medical information and so on. So these are two areas that I look at and, working across the team to try to build solutions and also with the ecosystem come up with solutions that are interesting for these areas.
Yeah, fantastic. Two very important areas of application there. Okay, before we wrap up, is there anything else that you wanted to add?
Yeah, I think just to kind of wrap things up, as I was thinking about this interview, I was having discussions with some of my colleagues and friends, and I realize how important it is to, in the next 5 years or so, to turn devices into more private and more contained compute. I think with what's happening with, generative AI, we're going toward an era where devices are going to have agents that are acting on our behalf continuously without us even telling them what to do and collecting data when we're attentive and we're ready, we're going to get that data. So this provides an opportunity for us to structure this compute from the ground up in a way where the user data is private, the user data is secured. And it's, having us reimagine this edge compute devices and how they're gonna operate. And so Lattice's role in terms of connectivity to sensor and processing right next to the sensor, I think is going to be pivotal in building smart devices at the edge in the future.
Yeah, fantastic. It's certainly a very exciting space to be working in at the moment. So thank you very much for taking the time to share your insights with us. It's been a pleasure having you as a guest.
Thank you, Paige. I appreciate the, opportunity to come here and talk to you.
You're very welcome.
Thank you for listening to this latest episode of Electronic Specifier Insights. Don't forget to subscribe to the series to keep up to date with our newest guests, and do share with fellow colleagues, friends and family who may be interested in the latest news from the electronics industry.